Why does oil not freeze like water? If you place a bottle of water in a freezer, it turns into solid ice. The change is dramatic and familiar. But if you place a bottle of cooking oil in the same freezer, something different happens. It may become thicker. It may turn cloudy. Some oils partially solidify. Others remain mostly liquid. They rarely form a clear, rigid solid like ice. The reason oil does not freeze like water is not that it cannot freeze. It is that oil and water are fundamentally different at the molecular level. Freezing depends on how molecules arrange themselves as temperature drops. Water has a simple molecular structure. Each molecule contains 2 hydrogen atoms bonded to 1 oxygen atom. This shape allows water molecules to form hydrogen bonds with each other. These hydrogen bonds create a highly organized network when water freezes. As temperature decreases, the molecules slow down and lock into a repeating crystal pattern. That pattern forms ice. The structure is stable and uniform, which is why ice appears as a solid block. Oil is not a single substance like water. Most oils are mixtures of many different molecules, primarily long chains of carbon and hydrogen called fatty acids. These molecules are larger and more complex than water molecules. They do not form strong hydrogen bonds with each other. Instead, they are held together mostly by weaker intermolecular forces. Because oil contains a mixture of different fatty acids with varying shapes and lengths, the molecules do not align neatly into one uniform crystal structure. When temperature drops, some components may begin to solidify while others remain liquid. This produces a gradual thickening rather than a sharp freezing point. Water freezes at a specific temperature because its molecules are identical and organize consistently. Oil does not have a single freezing point because it is a blend. Different fatty acids solidify at different temperatures. Saturated fats, which have straight molecular chains, can pack together more tightly and solidify more easily. Unsaturated fats, which contain bends in their chains due to double bonds, cannot pack as tightly. These bends prevent neat alignment. As a result, oils high in unsaturated fats remain liquid at lower temperatures. This is why olive oil may become cloudy in the refrigerator but not completely solid. The cloudy appearance comes from certain fats crystallizing while others stay fluid. There is also a difference in polarity. Water molecules are polar, meaning they have regions of partial positive and negative charge. This polarity contributes to strong intermolecular attraction and structured freezing behavior. Oil molecules are nonpolar. They do not attract each other in the same organized way. Without strong directional bonding like hydrogen bonds, oil molecules do not form a rigid, open lattice structure as water does. Instead of snapping into a defined crystal, they gradually lose mobility. Another reason oil seems not to freeze is visual expectation. Ice expands and becomes opaque or frosty. It looks obviously solid. When oil cools, it may simply become viscous. The change appears subtle, but chemically, parts of it are indeed solidifying. It is just happening unevenly across different components. In industrial settings, oils absolutely can freeze. Certain refined oils or pure fatty acids have measurable melting points. But in everyday cooking oils, the mixture makes the transition less dramatic. The difference between water and oil in the freezer is not about resistance to freezing. It is about molecular uniformity. Water molecules are small, identical, and capable of forming strong, ordered networks. Oil molecules are larger, varied, and less capable of organized bonding. So, water forms a crisp, defined solid at a precise temperature. Oil thickens, clouds, and sometimes partially solidifies over a range of temperatures. Once you understand the molecular structure, the mystery disappears. Oil does freeze. It simply does not freeze in the clean, structured way that water does. If you found this explanation interesting, the next story explores another everyday liquid that behaves very differently under temperature change than most people expect. Click on the channel to discover more untold stories behind simple things.